in this certain situation, we have an airplane. It's traveling a speed of 500 miles per hour, heading north 30 degrees west at a fixed altitude. The plane encounters a wind blowing with a velocity of 70 miles per hour in the direction of north 45 degrees east. What are the resultant speed and direction of this plane? So kind of what we have going on here is this plane is using its engines to go 500 miles per hour in a goal direction of north 30 degrees west. However, also acting upon this plane, besides its own engine, is wind. And this wind is going to blow this plane off course a little bit. It's going to impact the speed of the plane and the direction of the plane. So here they're asking me for what's the resultant speed and the direction of the plane. That is, how fast is this plane actually going? And in what direction is it going? So we can think about this like a vector equation. And I'm just going to write it really casually in words. This is how I think about it. I think about it as we've got this plane and it encounters this wind. And then we get this resultant. What happens because of that? Now, I will tell you, you're going to see some vocabulary that comes along with this. A lot of times when we talk about a plane and this 500 miles per hour business, you might see things called airspeed. They might use that word in the context of this problem. So how fast is this plane going relative to the area around it? Right? What are the engines capable of doing? Then in this resultant, you might see something like ground speed. So imagine we've got these air traffic controllers that are sitting in this tower and they're monitoring the positions of these planes. The ground speed is measuring the actual speed relative to the ground of this plane. So it would see the impact that the wind has on this plane. I do think it's helpful to sketch a quick picture, a quick illustration, nothing fancy. But if I'm going to do components, what that means is I might sketch a vector for each one of these pieces that I have information about, and separate pictures. So I'm not using tip to tail here. And as I draw my first vector from standard position, this idea of initial point at the origin, I'm thinking about rotating from north. Look at that direction. North 30 degrees west means from due north, rotate 30 degrees towards west. So indicating initial point at the origin, terminal point here, the arrow showing the direction, and I can label some elements here. This angle between north and my vector, that measures 30 degrees. I also can label the length of this vector with our magnitude. And I want to say this, and it's going to sound a little bit confusing. Remember, we conceptualize the magnitude as the length of this vector, but notice the units on this magnitude aren't units of length, right? It's units of speed, or it might be units of tension. But visually, we see magnitude as the length of the vector. I can do the same thing again for my wind vector. The plane encounters a wind blowing with a velocity of 70 miles per hour in the direction of north 45 degrees east. And because it's 45 degrees, they could have just said northeast. They could have just said northeast. That would have meant exactly north 45 degrees east. I'm going to draw that vector. Initial point, terminal point, the arrow. And that north 45 degrees east is really indicating this angle up at the top between north and my vector. And I can label the magnitude 70 miles per hour. Again, I'm visualizing that as the length. And don't worry, it's not drawn to scale, and I'm okay with that. Now, I'm not personally going to draw the resultant vector because I don't know what it looks like. I don't know what it looks like. But here's why I think the picture is important. When we talked about our formula that we can use for efficiency around calculating components, I indicated that that formula said, let's take the magnitude of our vector times the cosine of our angle, and then the magnitude of our vector times the sine of our angle. But that angle has to be our angle in standard position. We were not provided with our angle in standard position. We were provided with our angle in the context of north, south, east, and west. So in order to do our calculations, we have to decontextualize this information. The picture can help me do that. So I know that this vector is located at north 30 degrees towards west, but when I calculate, I'm going to calculate using my angle in standard position. So I can visually see that as I went 90 degrees and 30 degrees more. The angle I'm going to use for theta is 120 degrees. For my second vector, I get lucky in the context that it's 45 degrees here, but I still want to make sure that I'm looking at my angle from standard position. So from the positive x-axis, rotating towards my vector, that angle in standard position that I will use for theta is 45 degrees. But once we have that, we can quite efficiently start calculating our components for each one of these vectors. So using my formula up there for my plane, I have a magnitude of 500 miles per hour times the cosine of our angle in standard position, 120 degrees, and then 500 times the sine of 120 degrees. That will get my horizontal and vertical components for the plane. Then I'm going to do the same thing for the wind. And because I said I want to write this as an equation, I want to remember what this is going to provide me is my resultant vector's components. I'm just going to label that with components x and y. That's the mystery that I'm trying to solve. At this point, I would grab my calculator and I would start doing some number crunching. I've got 4 calculations to do. I would get negative 250 for my horizontal component, for my plane, and I would get approximately 433.01. Again, notice I'm taking this to the nearest hundredths, just trying to improve accuracy a little bit. And then for my wind vector, 70 cosine of 45, 49.5. And not surprisingly, I end up getting the same 49.5 for my vertical component. When I add these vectors together, I'm going to get the result of what the plane's trying to do, right, relative to the air, and what the wind is going to do. Together, it's going to determine my ground speed and direction. Adding together my horizontal components and my vertical components together, I will get the vector with a horizontal component of negative 200.5 and a vertical component of 482.51. Again, that's my horizontal and vertical components of my resultant vector. We know the components, so the goal is to turn this into a magnitude and a direction, and to communicate that in the context of the problem. Again, here's where I think a visual could be helpful. The hypotenuse of this right triangle drawn, using those components, represents the actual magnitude and direction of this plane. A squared plus B squared equals C squared. And if you trust me, when I solved this equation for the length of my hypotenuse, I got approximately 522.5. So again, I'm labeling that as the length of the side, but it really represents the magnitude. And in this context, that's the speed of the plane. But now I want to figure out the direction. And I want to think about this in the context of the problem. So every other direction that has been provided was in this context of north, south, east, west. So if I want to think about this angle right here, if I could quantify that angle, that would tell me from north, how far do I need to rotate towards west? If I could just figure out that angle right there. So from north to my resultant vector, how far did I rotate towards west? I'm going to figure out what is this reference angle of my triangle. Lots of strategies exist. Since I know all 3 side lengths of my triangles, you're going to find me using my tangent ratio. Tangent of that angle is the ratio of opposite over hypotenuse, or y over x, vertical over horizontal components. But notice again, I'm not putting the positives or the negatives. All I'm trying to do is to quantify this reference angle, and then I'm going to use the context of the problem to communicate my actual direction. And since I don't know this ratio at all, I'm going to use inverse tangent to help me reveal my angle measure. And when I do this calculation, I end up coming up with theta, the reference angle of my triangle, as 67.4 degrees. But I don't want to say at 67.4 degrees. What that is this angle in my triangle. So now it's time to recontextualize this problem. I want to communicate this angle from north. And I can come up with the fact that it's 22.6 degrees between my resultant vector and due north. So the direction would be north, 22.6 degrees west. This is how I would communicate the answer. 522 miles per hour at north 22 degrees west.